Okay, I will talk on introduction to nonlinear programming problem. Now, I will start nonlinear programming problem. All of you must have learned the linear programming problem. You have learned how to solve linear programming problem and basic concepts related to that. But nonlinear programming problem is something different. Different in the sense that for the linear programming you must have seen, if you know simplex algorithm and the other variations of the simplex algorithm, you can solve any linear programming problem with those. But nonlinear programming is not like that. Since here the nature of the functions are nonlinear and there are different kinds of nonlinear functions are there. Few functions are convex, few are not. That's why there is a set of solution algorithm for solving nonlinear programming problem of different kind. Now, we have designed the course in such a way that we will discuss the varieties of the nonlinear programming problems, and along with that we will discuss about the solution. That is why I will start with the basic structure of a nonlinear programming problem and solution of that graphically. Then I will move to the classification of nonlinear programming problem, and one by one I will give you the solution procedures, how to get the optimal solution for those. Now, this is the general nonlinear programming problem, where you see the structure of the nonlinear programming problem is that the objective function we have considered as f(x), minimization or maximization of f(x) subject to a set of constraints. Now, here we have considered several functions. You see the functions f is there, that is the objective function, and there is a m number of inequality constraint. The functions are of gix rather, and there is a set of linear constraints as well, hjx, where j is running from 1 to L. That means there are m number of inequality constraints and there is L number of equality constraints. Along with that, there is a bound of the decision variable. Now, the decision variables may be restricted within certain range. That is why the bounds are given. If it is not given, generally, as you know, for the optimization problem we consider the non-negativity constraint for the decision variable. That means the decision variables can vary from 0 to infinity. But since we are considering the general form, here we have considered the lower bound as well as the upper bound of the decision variables. Now, this is the general structure of the nonlinear. If you look at the structure, you see the functions f, g, h, any one of these can be nonlinear in nature. This problem where at least one of the function is nonlinear, then we will say this is a nonlinear programming problem and our simplex algorithm simply will not work. We have to learn, you have to learn how to solve this problem. Now, for that I have taken few examples. With those examples I will try to explain you the concepts. Now, here I have considered a problem of two variables. Why I have considered two variables? Because the problem, then I can draw it, I can tell you how graphically we will get the optimal solution for this. Now, here you see the objective function, we are having the objective function which is circular in nature. The circle we have considered, that is the center 14 and 15, and there is a set of constraints. One constraint is of nonlinear, that is another circle with the radius 49 and the center is 8 and 9. There is a bound for x and there is a linear line x plus y less than equal to 24, but there is no bound for y. Once that there is no bound for y, generally we consider y is ranging from 0 to infinity. Let us try to draw this problem. You see, this is the axis for us. Now, we are first drawing the, as you did for the linear programming, same thing we will do, and we will draw the constraints one by one. First, we will draw a circle that is centered at 8, 9 and with the radius 7. All right. Now, this is the circle for you. Now, there is a bound for x, that is the lower bound of x is there, and the upper bound of x is also there, and there is a line that is x plus y equal to 24. Now, if this is so, the space, the points which are satisfying all the constraints, that will be the feasible space. You must have learned. That is why from here we can declare that this is the feasible space for us. That is why the optimal solution must lie within this. But you must be seeing the feasible space is bounded by the nonlinear functions, by the nonlinear curves, and this is not the case like linear programming problem. And in the linear programming problem, we have learned that always the optimal solution is at the corner point, or if there are infinite number of solutions, at least that is at the edge of the feasible space. Now, this is not the case for the nonlinear programming problem. Why this is so? If I just explain you this problem graphically, then you will understand. Now, let us consider the objective function. Objective function that is centered at 14, 15. That is why this is the center of the objective function, and you see these are the contours, the red circles are the contours of the objective function. That means the objective functions are moving forward. Okay. Then if I want to find out the minimization of the objective function, where I will get? Minimally, it can, once it is reaching to this point, we can get the optimal solution, because the objective function can go further and further, and at the minimum point I will get at this one. That is why we can declare that is the optimal solution, minimum optimal solution for this objective function. Now, let me extend this problem for the maximization type. That means the objective function can move further. What you have noticed here? You have noticed here that the optimal solution is not coming at the extreme points, or rather the corners of the feasible space. Rather, it is somewhere at the edge of the feasible space. That is why graphically, when the functions are very complicated in nature, that is the first problem for us to draw the function, and next problem for us how to get the optimal solution for that. That is another difficult part for us. That is why we need to learn. Graphically, this is a simple function circle. That is why we could find it out, otherwise very difficult for us. Now, I am extending this problem for the maximization type. That is why this objective function is moving further and further. What did you see? That once this objective function, the contour is moving, once this objective function is touching, that is the last possible position for the objective function to reach, to remain within the feasible space. If it goes further, it will be beyond feasible space. That is why if I maximize the objective function, certainly the optimal solution will come here. Okay, that is the, therefore we are getting the minimum is this point and the maximum is the other point. That is the beauty of the nonlinear programming, and that is a complex part as well. You need to learn how to solve it. That is why let us consider another set of problem. Now, in the linear programming problem, generally we are not considering the unconstrained problem in general, but you see for the nonlinear programming problem, we may consider the unconstrained, because you see this is a function is only given to you. Now, it has been said if x is in between certain range, there is a domain for x. Within this domain, within this interval, it is asking to you what is the where the function has the minimum. Okay, you have done in your school time this thing by finding out the differentiation of the function, but almost the same thing we will do. You see this, I have drawn the function here. Now, where is the minimum? This is the y, that is a function f(x), and this is for you x. Now, once you will get this point will be the minimum point. But if I ask you how did you get this point, then you will say that I have just done the differentiation of the function, from there we got the critical point and we got the solution that way. But this is not the case, where that we cannot do when the function itself discrete in nature. Alright. that methodology will not work. The differentiation can only be done if the functions are continuous, but if the function is not continuous, we cannot do it. That is why finding out the solution is not so easy for you. You need to learn how to find out the solution for it in general. That is the part you need to learn for it. Now, this is another function for you. This is also nonlinear in nature. What did you see in this function? If I ask you where is the minimum, you can say that there is a minimum point here, maybe minimum here and maximum here, because there are certain peaks over here. This is the function of the single variable, all right, and you see there are certain peaks. That is why in nonlinear programming problem there is a concept that is called the local optimal, that is called the global optimal. If I ask you in the domain of the function where is the maximum, you will say that this is the maximum point, and in the domain of function where is the minimum, there is the minimum. But knowing only the minimum and maximum will not serve the purpose, because I need to know even for, you see, once we are learning the optimization problem, this is a decision making problem, and this is very much related to the real life situation. That is why in the real life situation always that is very much related to the management science rather the business environment, when we need to take decision not only the maximum minimum, along with that we need to take the decision where the possible other peaks. That is why in the nonlinear programming problem there is one concept that is called the local minimum, local maximum. You see, I can say this is a minimum, local minimum point. This is also local maximum, but this is not a global. This is locally. Here there is a maximum, here there is a minimum, here there is a that is the global maximum. Now, here another global minimum, but here also we can have another local minimum. That way we have to find out not only the optimal solution, the maximum minimum, we need to find as well as the which one is the local optimal, which one is the global optimal. That is why you must be understanding, you need to learn the nonlinear programming in such a way, we need to have the solution, we need to get the optimal solution that is local as well as global. But it is sure that always we will try to get the solution that is global in nature, but all the solution algorithm will not give you that level. In all the time you won't get the global solution because of the complicated nature of the function. You have to be satisfied with the local optimal solution. That is why the global optimal solution and the local optimal solution both are important for us. Now, if you look at the function, what did you see other than this? You could see that there is a convex and concave nature of the function as well. That is why for learning nonlinear programming problem, once you are considering the nonlinear function, not only the local maxima, not only the global maxima or minima, always we need to, before to that we need to see what is the nature of the function, how the function is moving within the domain. That is very important for us. That is why study of convexity, concavity is also very important for us. Now, let us move to the function of two variables. If I move to the function of two variables, what did you see? The function, it is in the third dimension. There are also certain peaks are there. You can also define in the similar manner that there are certain local optimal points are there. These are the local maximum points, and this is the global maximum. This is the local minima. This is the global minima. If I just see the other part of the function, I could see even the local minima for this function. That is why once this is the function of single variable or two variable, we can visualize the local or global. But once the function is of, in reality, function is not of two variables. You will get the functions. Functions means, I mean to say the functions which are involved in the objective as well as in the constraints. These are function of several variables together. That is why you need to learn how to get the optimal solution for this. Now, then what is our objective? Our objective is to find out the optimal solution. Now, how to get it? If I just use your common sense, then very easily we can say that from the domain of the function I will pick up any point, I will check whether this point is optimal or not. If the function is at that point function is optimal, then we can declare this as optimal. That is why optimality criteria checking is the first criteria for us. How to check the optimality? This you need to learn, alright. And if the point is not optimal, then we have to move further, we have to search for the next and further, and that is why we need to move. That is why you need to learn that how to move to the optimal solution further and how to design the optimality criteria for the nonlinear programming problem. As I told you, the nonlinear programming problem involves different types of nonlinear functions. That is why optimal criteria also differs, but there is a general guideline that I will talk about it. Now, this is another very important part of the objective function. Before learning the convexity and concavity, you see there are certain peaks of the objective functions. That means the function is having the curvy nature. If the function is not having the curvy nature, that means function is linear. But if the function is having the curvy nature, then the next question is coming, whether function is increasing function or the function is decreasing function. If the function is increasing, whether it is a monotonically increasing or there is an ups and downs within the function or there is any value of the function within the domain. Okay. Not only that, we need to see how many peaks are there within that function and how many negative peaks are there within that of that function within the domain. All these things we need to learn. That is why there is a very important property in nonlinear programming problem, that is called the unimodality property. You need to learn what is unimodal function. Why I am talking about the unimodality? Because I will talk in detail in my next week classes, but now I will just mention the definition of the unimodality and I will tell you. If I refer to my previous example, you must have seen that we dealt with a function of single variable. How many modes it had? How many peaks it had? It had, for maximum there were 2-3 peaks were there, alright. Now, once that means if I have to find out the optimal solution, now we need to find out at which point the mode is there. It may happen that I will get one mode and I will declare this is the optimal solution, but it may happen there is a local for you. That is why what in general what we do, we break the whole domain of the function into several intervals, so that in each interval function is unimodal, so that in a better way we can analyze the function. That is why we will in different intervals we break the function and we consider function must be unimodal. Unimodal means there must be only one mode. If there is one mode, if that is the convex or concave in nature, then certainly we can find out very easily. That is why mathematically how to define the unimodality, let me first talk about it. Now, this is the monotonicity. As you know, a function f is monotonically increasing if I consider 2 points x1 and x2. Graphically I will tell you I will just show you in the next, and so that the x1 is the lesser than the point lower in the line, in the real line than x2, then function fx1 must be less than equal to fx2. Then we can say the function is monotonically increasing. Okay. And if this is the other case, x1 is lesser than x2, but fx1 is greater than equal to fx2, then function is monotonically decreasing function. Okay. Now, what about unimodality? As I said, there will be only one mode. Now, see within the interval a b, if I see that function is monotonically increasing in one side and monotonically decreasing in other side, or the reverse, monotonically decreasing in one side of a point x star and monotonically increasing in the other side of the x1, then we can say the function is unimodal. Once again I am repeating. Now, the function fx is unimodal within the interval a to b. The formal definition is that if and only if it is monotonic on either side of the single optimal point x star. I should not say optimal point. In general, let me just say any point x1, if I see in one side it is monotonically decreasing and the other side monotonically increasing, or the reverse one, then we can say the function is unimodal. I will show you the example of that. And unimodality is very important property, as I said, in the nonlinear optimization. All right, that's the definition. Now you must be seeing here the first example is a monotonically increasing function. If x1 is lesser than x2, if x1 is lesser than fx2, decreasing. If x1 is less than x2, x1 is greater than fx2, decreasing. And this is the unimodal function. That means, you see, there is only one mode within this interval. In one side it is decreasing, in the other side it is increasing. All right. Unimodality is very important property for finding out the optimal solution. Once again I am repeating. Now you see, this is another function of single variable. How many modes are there? In x1 there is a mode, x2 there is a mode for the minimum, x3 is maximum, x4 is the minimum. There are several modes are there. If I ask you to find out the optimal solution for this, then if you use your common sense, then what should be the case? You will start from here, you will search whether the function is monotonically increasing or not. If I move from here further, we will see function is increasing further. Okay, I will show you one example on that. You see, I am starting from here. All right. Now in this point I am here. Now I want to move on either side of this point. I can move this way, I can move this other way as well. In which way I will move? If I move right side, then I will be beyond the optimal points, is it not? I will search and search, I won't get the optimal solution at all, because function is constant further. That is why my search would be such that the procedure should not guide me to move in the right hand side. That is why I will move in the left hand side. That should be the right process for me. I am moving this way. Now the next question is coming, if I even move in the left side, how long shall I jump so that I will get the optimal solution? I do not know where is the optimal solution at all, because this is a simple graph is given to me. If I say you jump from here to here, you will get one optimal, but this is not the case in general. That is why I can jump from here to here, even I can jump further. Then what will happen? I will miss the optimal point. That is why you need to decide two things: from where I will start to get the optimal point in the real line. Not only that, how long shall I move so that I won't miss the optimal point. I will get the solution exactly, even it is local. Sometimes I have to be satisfied with the local optimality, because as I told you that local optimality is something that in many cases is serve the purpose. That is why instead of searching global optimality means I have to do more number of jumps, I have to do more number of iterations. In lieu of that, better let me be satisfied with the local optimal. All right. That is why there are several things to be considered. All right. That is just I wanted to. Now it may happen I will just jump up to this. In this way I will jump to the next, so that I can reach to x4 for finding out the local minimum point. That is the case. Now that is why, as I told you, just mathematically I have just written the steps. Just to see the steps, I will start from initial trial point, I will find a suitable direction, I will find out the appropriate step length, I will move to the next point. How? By considering the first point plus the step length as well as the direction together. All right. If I am moving to the left, direction will be negative. If I am moving to the right, direction will be positive. Now lambda is the second, that is the step length, sorry. Then I will get the next point. Xi will move to the xi plus 1. I will do the same process. Xi plus 1 will move to the xi plus 2. In that way, sometime I will get the optimal solution, but again the question comes. One by one the question will come, how to select the initial trial point. If the initial trial point is far from the optimal solution, then the number of iterations will be more. then I won't get the solution. That is why if I am, how can I use my common sense? But in science there is no space for the common sense. Always there is, it has been said that there is a guideline which one to be selected as the initial trial point. Alright, that is why you need to learn this one. The next you need to learn in which direction shall I move, how to select the direction. Now for the single variable case, if I say the plus minus, moving to the right, moving to the left, alright. But if you consider function of two variables, there are infinite number of directions from a point, alright. That is why with the plus and minus it will not work. It should tell me that in which direction shall I move, alright. I need to find out some direction. You have learned in mathematics the gradient of a function. That part I will consider it here, and I will define the direction and as well as the step length, and in this way we will move. This is a very basic idea how to solve a nonlinear programming problem, but this is not the case. This is not an efficient process to get. Just since this is the first class of yours, to have a feel how really we are getting the solution, just I have given you the feel of that. That is all. That is why you see few things we need to consider here. Up to this, from my lecture you must have realized that first part of nonlinear programming is that we have to judge whether the function is convex or concave. If the function is depending on the nature of the concavity or convexity, we need not to even judge the function whether we are getting the local optimal or global optimal. We can declare there are certain kind of conditions are there. There is a branch of optimization that is called the convex optimization. There is a branch of optimization problem, convex optimization, and in that convex optimization very easily we can say that always this methodology for this kind of problem will give you the global optimal solution. That is why study of convexity and concavity is very important for us. In the next class I will talk about it. Alright, modality, whether function is having unimodal or not, that is another part for you. Next thing you need to learn the gradient of the function. As I said, in which direction you will move, gradient will guide you to get it. Now since optimal are not restricted to the extreme points, that is why that is very difficult for us to get the optimal solution. There are infinite number of points at the edge of the feasible space. You know the extreme points are finite number of points, but here we are having the options that is infinite number. That is why which one will be the optimal solution, that is very important for us. We need to know. We need to distinguish between the local optimal and global optimal. That is why you need to know the definition of this mathematically. In the next class I will discuss about it. And it may happen the feasible space is disconnected. Feasible space is discrete in nature. You are getting the feasible space that is piecewise continuous. In one place continuous, in other place it is continuous. I will show you some picture of that. For example, if I just tell you the feasible space is like this, just you look at this. This is only the feasible space where I am giving the shade. This is not the feasible space, this is the feasible space. Then getting optimal solution, local, global, everything, study of unimodality, study of convexity, concavity, all these things you need to know together for nonlinear programming problem, and your differentiation will not work. You cannot find out the gradient. That is very difficult for you. That is why you need to know how to find out even for the disconnected space. Okay. Now these are the issues I will consider in the next class, and I will start my class with that. Thank you very much.